Welcome, class. Today we are going to start our discussion of Chapter 2. In this chapter, we're going to be looking at various aspects of measurement and problem solving. And at the end of the chapter, we're going to look at our first sort of real chemistry topic, specifically, and that's density. So let's get started by looking at measurement. So measurements are quantitative values, right? So when we are going through the scientific method, conducting experiments, data can be either qualitative, we typically call those observations, right? Or they can be quantitative. And so quantitative data is what we refer to as a measurement. And so measurements are, again, quantitative and have both a numeric portion, right, the number, the value, and just as important, they have a unit, right? And so as we go through this chapter and the whole course, we're going to keep emphasizing how important this idea of the unit is in the units and keeping track of our units. And so a unit is simply a standard agreed upon quantity by which other quantities are measured. So it provides a reference, right? A scale, if you will, right? If we're measuring something in inches, right, that gives us an idea of how many inches it is, right? So we can, that inch is our standard quantity that we're quantifying against. And to have a real measurement, to have a valid measurement, it not only needs that numeric value, but it also needs the unit so that we know what we're comparing it to. Now, in this segment, we're going to talk about the idea of scientific notation, and in our next video, we're going to pick up and talk about significant figures, two important concepts when we get to understanding measurements. So let's turn our attention to scientific notation. So scientific notation is a useful method to express large and small numbers in a more compact way, right? So oftentimes when we make measurements, maybe those values are very tiny, or maybe they're quite large. And so sometimes it's useful to be able to display that in a way that is easier to reference, right? In a more compact form. So, for example, if we take this number here, 0.0000000012, right? This is kind of an awkward number, right? The mind or the brain, right, makes it easier to understand numbers that are of sort of reasonable quantities. Tens, hundreds, ones, tens, hundreds, right? These are sort of easy for us to compare and understand. When we start getting to these very tiny numbers or even very big numbers, it becomes harder to sort of understand those or to compare those in a meaningful way. So when we think about scientific notation, there's two parts, right? We have the decimal part and the exponential part. The decimal part should be a number between 1 and 9.999. In other words, there should be one digit to the left of the decimal place when we're finished. The exponential part is going to express how many places we had to move the decimal place in order to get to this decimal part. So if our exponent is a positive value, that means our decimal, right? Our decimal number is multiplied by 10 that many times. So what that means is our original number is a number bigger than 10. For example, 1,234. When we put that into scientific notation, it results in a positive exponent. A negative exponent indicates that in order to get to our decimal part, we had to divide a number by 10 n times, right? Where n is the value of our exponential part. So what that also means is that the original number that we're dealing with was less than 1. So for example, 0.01234, right? Putting that into scientific notation would result in a negative exponent. Now, one last point about the decimal part is that it should contain all of the significant figures in our measurement. And we'll elaborate more on what we mean by significant figures in our next segment. So, how exactly do we get a number into scientific notation? Well, we got a couple steps here. The first one is to move the decimal point to obtain a number with one digit to the left of the decimal place. So this is how we're going to get the decimal portion. And then we're going to write that result times 10 raised to the exponent, and that exponent is the number of places we move the decimal point. And again, if the exponent is positive, that means you moved the decimal place to the left. For example, if we had the number 5,983, to get one number to the left of the decimal, we had to move the decimal place 1, 2, 3 place times, and so our exponent becomes a positive 3. If the exponent is negative, if you had to move the decimal place to the right to get one digit to the left of the decimal place. So for example, if we had the number 0.00034, we had to move the decimal place 4 times to get one number to the left of the decimal place, and so as a result, our exponent is negative 4. So let's do a couple quick practice problems here. So if we have the number 0.0000380 meters, in order to get this one number to the left of the decimal place, we have to move the decimal place 1, 2, 3, 4, 5 spots. We had to move it to the right, so that means our number is going to be a negative exponent. So what we get here is 3.80. So notice I include all these numbers here, times 10 to the negative, and again that was 1, 2, 3, 4, 5 spots that we had to move it. So 3.8 times 10 to the negative 5th meters here. Now, if we look at a very large number, right, to get this into scientific notation, again, we're going to move the decimal place, but this time we have to move it to the left. So we have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spots. So in this case, our decimal portion is going to include all of the non-zero numbers, 1.8416 times 10. It's going to be a positive number because we moved it to the left, and that positive number is going to be 13 because we moved it to the left. So, scientific notation and a few examples of it. In our next segment, we're going to move on and look at significant figures and how we determine how many significant figures we should be displaying right here, or in any number for that matter.